Okay, welcome back. We're going to go through an example, a question from the 2019 exam in this course. There were two questions in the exam. You had 2 hours to do it. I'm going to go through the first question, which has to do with bosonic superfluids and Ginzburg-Landau theory and other related topics. I'll go through it somewhat briefly. Some of the questions are very, very closely related to homework questions. So, I'll probably sketch them because you'll have chances to do them on the homework and to ask the teaching assistant about them. But anyway, so here we go. Question 1, 4 marks. Give a definition of Bose condensed. Oh, and you can download the exam from the web, incidentally, if you don't already know that. It might be useful to do that, follow along. But I'll write out the questions here so you'll be able to see them. Okay, question 1. Give a definition of Bose condensation and explain how it differs from superfluidity. Okay, so a minimal answer, which is a reasonable minimal answer, is the following. Bose condensation, BEC, is macroscopic occupancy of a single orbital at some t below Tc but greater than 0 occurs for non-interacting boson. For non-int bosons. Actually, I'm not even sure that last phrase is even required. Superfluidity equals it's defined by the phenomenon If anyone even knows that reference, I'll be impressed. Phenomenon of superflow. In other words, lack of viscosity, no viscosity, or dissipation. This is not true of a BEC. Not true of BEC, but is true for weakly interacting, weakly int repulsively interacting Bose gas. Actually, it's not even necessary to have that last phrase. I think the first phrase is probably sufficient, but it's nice to have these comments. There's lots of other differences that you could point out. You could point out, for example, BEC does not have a divergence in its specific heat at the critical temperature, whereas superfluids typically do. But that's not really required. Okay, so that's question 1. Okay, that should have been the easy one. Question 2. Consider a gas of n non-interacting spinless bosons moving in d dimensions with dispersion relation epsilon equals alpha times k to the 4th, where epsilon is an energy and k is the wave vector. For what value of the dimension d do you expect the system to exhibit Bose condensation at sufficiently low but non-zero temperature? Okay, so the easy way to calculate this is to occupy orbitals with the Bose factor and see if there's enough space without macroscopically occupying the zeroth mode. Okay, the zeroth mode is special when there's Bose condensation, but if you can occupy all the if you can accommodate all of the particles without macroscopically occupying the zeroth state, then you don't have Bose condensation. So let's just write out an expression for thinking that there's no condensate, and see if we're possible to accommodate all of the bosons that we have. So this will be the number of bosons is the volume of the system, the usual d to the d, k over 2 pi to the d. Then the Bose factor of beta epsilon of k here. So it's this factor here. I guess what we're really interested in here, we can drop the all the prefactors, which aren't going to be too important. So it's integral d to the d of k, d-dimensional integral, k, and then 1 over e to the, well, okay, so what's going to be upstairs here? So this is going to be the Bose factor, so it's alpha times beta times epsilon of k is k to the 4th, or maybe I should have written it the other way. There's beta here for temperature, then there's alpha, this factor, alpha, and then k to the 4th upstairs, k to the 4th minus 1. And the place where this quantity can get large is near k equals 0. So let's consider what happens near k equals 0, or at so this, okay, and near k equals 0, then we have this quantity going as, integral ddk. This near k equals 0, we can expand this, and so expanding this exponent, this goes 1 plus beta alpha k to the 4th plus dot dot dot. The 1 here cancels this minus 1 here, and we're left with 1 over k to the 4th here. Okay, and so this diverges. So the integral diverges at small k for d less than or equal to 4. Okay, so in d less than or equal to 4, you have a divergent, you can accommodate a divergent number of bosons. So no matter how many bosons you put in to the system, you can always accommodate them for d less than 4. However, for d greater than 4, what you get is finite. D greater than 4. Oops. Come back. Oh my gosh. Come back. There we go. For d greater than 4, you get a finite integral, which means at certain densities and temperatures, you cannot accommodate all of the bosons without macroscopically occupying the k equals 0 state. Okay, so that means that there's only BEC occurs only for d equals 4. Okay, good. Yeah. Right. Okay. Next question. Now assume instead that the n bosons in the system interact with each other via, let me bring this down here so you can see it, interact with each other via short range repulsive interaction. So the Hamiltonian is given by, it has the kinetic term here, alpha k to the 4th, plus the repulsive term u times d ri minus rj, delta function, with u greater than 0. Rewrite this Hamiltonian second quantized form using the bosonic operators satisfying the usual bosonic commutation relations. Well, this is something that we could do just by inspection. So let's do it just by inspection. ddr psi dagger del. Okay, so the kinetic term is alpha k to the 4th, so we can just write that as alpha gradient to the 4th of psi. These are operators like this, and then plus u, the usual u over 2, then psi dagger squared psi squared. I guess all of these are at r, at position R. Okay. Now, the interaction term is exactly the same interaction term we've used all along. The kinetic term is slightly different. Instead of being a k squared term, it is now a k to the fourth term. So instead of a minus del squared, it is a del to the 4. Okay. There's several ways. I mean, this is all that's required, actually, just to write it down. But if one wanted to be more definitive about it, there's several things one could do. For example, one could have said, well, let's look at the interaction term, int, and we can rewrite that in more of a continuum form as integral dr, integral dr prime, density at position r, u of r minus r prime, density at position r prime. We could then use the well, it's a little tricky here because you notice that this is u here is written as I less than j, and a nicer way to have written this would have been to write it as u over 2 sum over I not equal to j times the delta function ri minus rj. So let me draw that again so you can see it. So this would have been nicer if we wrote this term as u over 2 sum over I not equal to j, that of the delta function of ri minus rj. The I less than j gets rid of the factor of 2, but it's actually nicer to write it this way. So there is in this expression down here, there should be a 1/2, representing that 1/2 here. We can let the delta function act, and then we get 1/2 integral dr rho of r squared, and I guess times u back up, times u out front, and rho of r is psi dagger of r psi of r. These are all hats. Psi dagger hat psi of r. And so we just plug this expression, the psi dagger psi, into here, and you get almost this, except this one has been normal ordered. And the normal ordering, as we mentioned in the lecture, is there to assure that one particle doesn't actually interact with itself. It's arranged here so that you require two particles to have a non-zero interaction. You have to destroy two particles and then put them back in order to get something non-zero. If there's only one particle in the system, the interaction term is 0 if it's normal ordered, but it's non-zero if it's not normal ordered. Actually, I believe the markers last year did not deduct for people not normal ordering, although most people, if I remember correctly, most people did end up normal ordering anyway. The reason why you wouldn't want to deduct is because it only makes a correction of order 1, whereas usually when you're considering Bose condensation, there's n particles in the system where n is a huge number, and you're only making a mistake of a single particle. Okay, so that gives you the interaction term. If you want to think about the kinetic term, maybe the kinetic term, maybe a nicer way to have written it would have been sum over k alpha k to the 4th c dagger k ck. That's a natural way to write this, and then we can Fourier transform the c operators back into the psi operators. This is a standard trick. Just switch to momentum space or the eigenspace of the operator we're interested in, and then convert back to the to whatever basis we're interested in. Okay, that's so much for that question. Okay, question part D. We're going to have no trouble making it through this exam in 2 hours, I think. I do have to. I have to admit that despite the fact that if you really know what you're doing, you can get through these exams rather quickly. I've sort of always complained that the exams are too long because I'd really rather someone is tested on what you know rather than how fast you can reproduce it. But this just seems to be the way with people who've been at Oxford for a while, realize that a lot of exams are under time pressure, and that's just how it is. So someday maybe this will change. Okay. All right, so part D. Using the equations of motion, just the Heisenberg equations of motion here, for the operator psi hat, derive a time-dependent Gross-Pedievsky equation for the system. Here, what we're going to do is we're going to actually use the Hamiltonian from the that we wrote down previously here. We're going to use this Hamiltonian, and we're going to commute it through to get a Gross-Pedievsky equation here. Now, the Gross-Pedievsky equation should be written in terms of a classical field rather than an operator, and the classical field should be normalized, so this psi squared is the boson density at position R. It's what we've been doing all along. Make sure to explain how one gets to the classical field from the quantum operator. Okay, so the first thing to do is to actually put in our Hamiltonian here and perform the commutation. So we know what the commutation relations are for the psi field. They're given to us. We know what H is because we just derived H here. Oops, come back. We just derived H. Come back. Okay. We just derived H. So we can do this commutation. And if we do it, I'll just do it quickly here. We get d psi hat of R dt is alpha, gradient to the fourth, plus u psi dagger hat of R psi dagger of R times psi dagger hat of R. Notice that in doing the commutation, you had to commute psi with two different psi daggers, and that means you lose the factor of 2, which was here, the u over 2, which was sitting here, because you have to do you had two operators, you kill one of them, but there's a choice of which two you kill. Now this is not the result we want because these things are operators. These psi things are operators, but we know how to go from operators to scalars, and the way we do that is we use, well, one way to do that, there's many ways to do that, but one way to do it is to use trial states, which are coherent states. So let's write, there's various different ways we can play this game now, but let's write an operator. Phi hat is d dimension R, wave function phi of R, and then the operator psi hat dagger of R. So this actually probably I should have written this as dagger like this. So this is the operator which creates a particle in the orbital phi. Okay, so this operator, this is an orbital phi, and this is an operator creates a boson in orbital phi. Okay, good. And we can take this phi to be normalized, a normalized orbital. So integral dr phi squared equals 1. And then we can write our trial state. Trial state, a little smaller so you can see it. Our coherent trial state. Coherent state is e to the, well, I'll write this as square root of n phi dagger hat on 0. This is not a normalized trial state. If I wanted to normalize it, I would write e to the n over minus n over 2 to make it normalized. Okay, and then the effect of taking the expectation of this equation of motion, this operator equation of motion, in this coherent state is to replace, the effect of this is to replace psi hat operator with psi, scalar, which is the square root of n times phi. Okay, so if we do that, we just replace this equation with exactly the same equation. So let me just copy it. Copy and paste. Oops. Oh dear. Didn't want to do that. Let's try it again. Take this equation, copy it, put it here, paste it. Here, I'm going to write the exact same equation. The only thing is I'm going to erase the hats. So this is now a scalar equation for psi. Okay, so we get a time-dependent Ginzburg-Landau equation, or a Gross-Pitievsky equation for our order parameter psi. The only thing different from our usual Gross-Pitievsky equation is that we have a different kinetic term here. Okay. All right. Part E. The ground. So we're going to need this Gross-Pitievsky equation below. Okay. Next part. The ground state is given by absolute phi equals phi naught is a constant. Write a low energy excitation at wave vector k in this form. So it's a constant. There's a time-dependent oscillation associated with the chemical potential. That's basically the eigen. You can think of the chemical potential as just being the eigenvalue of the energy. So it's just e to the I omega t oscillations. There's the constant term, and then there's a k part, which is e to the I k dot r minus I omega t, e to the minus k, psi minus k e to the minus I k dot r plus I omega t. So we're here assuming that psi of k and psi of minus k are both small. We want to substitute this into the Gross-Pitievsky equation to calculate the low energy excitation spectrum of this interacting Bose gas. This is almost identical to the exercise we do in homework. So maybe I don't want to give you too many hints on how to do it, but maybe I'll give you some hints how to do it. For people who are watching ahead in the lectures, so you get some clues here. So the first thing to do, okay, let's take our equation. We're going to need this equation. So again, copy it, bring it down here, paste. Okay, so we basically, the whole game is just to plug this form into this equation and expand, keeping in mind that these psi's are small parameters and this psi naught is big. So the leading term is going to come from things that only hit psi naught. So on the left, there's a time derivative that's going to pull out a mu, and on the right, the only thing, well, there's no spatial derivative of psi naught, but there's a u psi squared term here on the right, and both the left and the right are going to be multiplied by a psi naught. So you end up getting h bar mu naught psi naught equals u psi naught squared times psi naught. Nice equation. We can then cancel one factor of psi naught. That is useful. So we get h bar mu naught. Mu. There's no naught on the mu. H bar mu is just u times psi naught squared, which is the superfluid density. I guess we call it the superfluid density n. Well, okay, let's call it rho. Okay. So we have this as the first step. This next step is to look at linear order in these factors psi k and plug those and plug this equation into the Gross-Pitievsky equation here and pull out all terms which are linear in psi k or psi minus k. And if we do that, maybe it's not worth doing algebra in too much detail here, but if you do that, the equation you get is h bar mu plus omega psi k equals alpha k to the fourth plus 2u psi naught squared. Well, here I've assumed psi naught is real. Assume psi naught is real. We always do, don't we? Psi naught squared, psi k plus u psi naught squared times psi minus k star, and then h bar u minus omega psi star minus k equals same alpha k to the fourth plus 2u psi naught. It's really worth working through this yourself if you haven't done so for the homework. Psi k. So what we're doing here is we're identifying prefactors of terms that look like e to the I k dot r minus I omega t, and prefactors of terms that look like e to the minus a k r plus I omega t. And pulling out all the factors of one gives you the first equation. Pulling out all the prefactors of the other gives you the second equation, at least at linear order in these psi's. So we then can recall this identity here, these identities up here, which allow us to replace, I guess, 2u psi naught squared with h bar mu times 2, I guess. And we can then rewrite these two equations as a matrix equation, which I'll write like this: omega psi k psi minus k star equals, I guess, alpha k to the fourth plus u rho, and then u rho on the off diagonal minus u rho on the off diagonal minus alpha k to the fourth minus u rho here times psi k psi star minus k. And this is an eigenvalue problem for the frequency omega, or the energies of the system. You can just solve for the eigenvalues of this matrix to get omega is square root of alpha k to the fourth, alpha k to the fourth plus 2u rho, and that's the excitation spectrum. So this is the analog of the Bogolubov excitation spectrum for a Bose gas whose spectrum is k to the fourth rather than k squared. And you should recognize this as looking a lot like the Bogolubov spectrum that we calculated in class, and also that you do for homework. The only difference being that the kinetic term is alpha k to the fourth instead of h bar squared over 2m k squared. Okay, last part. Given the dispersion relation that we just derived, that would be this one, do you expect the system will be superfluid? Justify your answer. Well, let's just check this. So it's small k, omega goes as k squared, right? I mean, there's a k to the fourth sitting out front. It gets square rooted, and you can throw this away. And so this is a constant, so it just goes as k squared. And that violates, fails the superfluidity criterion, fails the Landau criterion. So this is like a free particle in a BEC with the usual quadratic dispersion. There's no sound mode velocity. There is no velocity below which the superfluid can flow without creating these excitations. So we expect this is not a superfluid in terms of flow. And that is the end of this problem. I'll do the other problem from the exam I'll do later on when we cover that material. Okay, see you next time.